Hello everyone. The title of this video is Identifying Power Functions. Alright, so every example I'm going to do in this video is taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 5.2, called Power Functions and Polynomial Functions. And I'm under the heading Identifying Power Functions. Alright, so each example I'm going to work on in this video is either going to be an example from the reading or one of the try it problems from the reading, or one of the exercises at the end of the section related to this particular objective. Okay, so the first one I want to do is example 1 from the text. Right, so let's take a look back at the text. Again, you got some reading to do in their definition of a power function. It's just a single term expression with a real number times the input variable to a real number power. That's it. Alright, so example 1, just identifying power functions. Which of the following functions are power functions? And these are a lot of the functions from that toolkit list, right? That list of the toolkit functions or the library of functions, whatever we call them. And what we're going to notice, what I'm going to show you, is that every single one of these, by their definition here of a power function, every single one of these is a power function. Okay. So again, I'll write up the definition of a power function. Power function is simply y equals or f of x equals, or whatever you want to call it, right? If you use function notation. And I'll write it the way they have it in the text, as some number k times x, right, times the variable, the input variable, to some power p, where k and p are real numbers. Right? Any real number. And I guess 0 would be included in there. If k were 0, you have y equals 0. That's just a horizontal line, right? That's the x-axis. Alright, so for example, going through this list in example 1, remember the constant function, f of x equals 1. And you might ask, they're asking, is this of this form? Well, yes. You can express 1 as 1 times x to the 0 power, if you wanted, right? Remember, anything to the 0 power, anything that's not 0 to the 0 power is 1, right? And then we could just define the value at x equals 0 to be 1 if we wished. And this is a power function. And like I said earlier, we're going to see that every single one of these in this list they're giving us here is a power function. The next one, f of x equals x, the identity function. Well, again, it is definitely of this form. This is 1 times the input variable x to the first power. See, the k and the p are both 1. So it is a power function. Let me actually spell it correctly. That's an f, sorry. The next one is the square function, right? F of x equals x squared, the most basic quadratic function. Is this of this form? Absolutely. It's just, the 1 times x to the second. It's a number times the variable to a power. That is a power function. So k is 1, right? The coefficient, and p is 2. So I'm just going to do this, a power function, ditto, 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 right? Then the cubic function, right? The most basic cubic function, f of x equals x to the third. Well, absolutely, right? It's 1 times x to the third. A number times the variable to a power. Power function. And then they start doing this. F of x equals, remember that reciprocal function, 1 over x. All right, now you might be thinking, this does not look like that. Well, it doesn't right now. But hopefully you recall your negative exponents, right? 1 over x is the same thing as 1 times x to the negative 1. And look at that, it's exactly that form where k is 1 and p, the power on x, is negative 1. That's still a real number. So by their definition, this is a power function. Then f of x equals, the reciprocal squared, right? 1 over x squared. Same thing, I'm hoping you remember your negative powers, right? This is 1 times x to the negative second power. A number times the input variable to a power. This is a power function. All right, then they get into some roots, right? The radical functions. F of x equals the square root function, right? The square root of x. Now again, it doesn't look like a power function right now, right? Doesn't look like that form, but I can, hopefully you remember your fraction powers, right? Negative powers and fractional powers. I'm hoping you remember all that stuff. Because this is the same thing as 1 times, and then the square root of x can be expressed as x to the 1/2 power. So I have a number times the input variable to a real number power. This is a power function. And then the final function in that list is the cube root. Right, the cube root of x, same thing. This is 1 times x to the 1/3 power. Again, it can be expressed as a number times, just the input variable to a real number power. So all those functions in that list are power functions. And let me take a look at let me show you what the graphs of these look like. All right, so I'm gonna go to that free online graphing calculator site, desmos.com, and we'll put in f of x equals, I'll just do x to the p, all right, x to the p. And I'm going to add a slider for p, and I'll just change the value of p around. Now see, when p is 1, you get the linear function, right, the identity function, y equals x. Then I can change p to 2. You get a parabola, right, y equals x squared. Change it to 3, y equals x cubed, the cubic function. Right, and then going backwards, right, when p is 0, it's just y equals 1, right? The constant function, I showed you that earlier, right? X to the 0. And then x to the negative 1 is the reciprocal function, right? 1 over x. X to the negative 2 is that reciprocal squared, right? 1 over x squared, x to the negative second. And you've seen these graphs before. But did you notice how there was still a graph for these functions even in between, right? X to the 1/2, right? If I go to 0.5, that's the square root function. All right, that's the square root function, x to the 1/2, square root of x. And I can let this play, and you see how the graph changes as powers change. Right? Now, it changes kind of dramatically when you're in the negatives, but a little less so in the positives. But all these are all of these graphs you're seeing flash before your eyes are power functions. All right, of some number, which I just have the number 1 here as the coefficient, times x to a real number power. All right, and this is only going from -10 to 10. I could increase the range if I wanted, but let's pause it here. Right, so there's x to the 7.5 power. Right. And we'll talk much more about the graphs of these in future videos. Right, I just wanted to show you these right now in the beginning. All right, so that's it for my first example. And then the second example is just asking, you know, which of these are power functions. All right. So which of these functions I have here, and I have a big list, can be expressed as a number, a real number, times just the variable, right? Just x, or if the variable's t, just t. You know, whatever the input variable is to a real number power. Okay. Can these be expressed that way? Well, so I'll keep the whole power function definition up top. And first one, f of x equals, now it's 2 times x times 4x cubed. If you were to simplify this, right, actually multiply these, you have 2 times 4 is 8. And then x times x cubed would be x to the 4th. This is a power function. All right, you see the output is just a number times the input to a power. Right. So k would be 8 and p would be 4. So I'm going to circle that. All right, that's a power function. And I'll put just a big X through ones that aren't power functions. Now how about g of x here? G of x is -1 times x to the 5th. Now, if that was all that was there, that would be a power function. But there's an additional term, plus 5x cubed. Now again, if that were alone, if it was just 5x cubed, that would be a power function. But the sum of them together does not look like this, right? It's the sum of two power functions, but it together is not a single power function. I hope that makes sense. So I'm going to put a big X through that one. That is not a power function. All right, now the next one's definitely not. H of x equals, I have a fraction, 2x to the 5th minus 1 in the numerator, divided by 3x squared plus 4 in the denominator. This, you can divide, do polynomial division here, but you're going to see there's no way to write this as just a number times x to a power. All right, so this is not a power function. Okay, how about this? J of x equals, x to the 5th. That is a power function. It's 1 times x to a power. Number times the input variable to a power. So this is a power function. How about this one? K of x equals, now it doesn't look like it yet, but x squared to the 3rd, when you use properties of exponents, this is x to the 6th power. Remember, when you have power to a power, you multiply those exponents. And this is 1 times x to the 6th, a number times that input variable to a power. So this is also a power function. Now for this next one, L of x equals x minus x to the 4th. Kind of like my g of x earlier, each individual term would be a power function, right? If I just had L of x equals x, that would be a power function. If I had just L of x equals negative x to the fourth, that would be a power function. But we have here, the sum of two power functions. That's not on its own a power function. I can't write this as a number times just x to a power. So that's not a power function by definition. All right, it's the sum of power functions, but not itself a single power function. Okay, the next one. This here is kind of like the h of x earlier. You got x squared divided by x squared minus 1. Now, again, you could divide these. If you were to do some division, this would be 1 plus 1 over x squared minus 1. If you did polynomial division, got a quotient plus remainder over divisor. But still, there's no way I can write this as just a number times the variable to a power. So this is not a power function. Now how about this one here, p of x equals, now if it was just 2x, that would be a power function. But it's not, right? There's all these other factors. Times x plus 2 times x minus 1 squared. And if you were to multiply all this out, you'd get a bunch of terms. Each term would be its own power function, but remember from earlier, the sum of power functions, right, like this g of x earlier and L of x, the sum of power functions doesn't make a power function. Right? I cannot express this as just a number times x to a power. Right? So because I can't do that, not a power function. All right, and then this last one, q of x equals 3 to the x plus 1, which could also be expressed as 3 times 3 to the x. Remember, when you multiply things with the same base, you would add the powers, 3 to the x plus 1. Now this is not a power function. This is called an exponential function. And we'll talk about those in a later chapter, later videos, but this is just the other way around. My power functions have a number times, a variable to a number, a variable to a power. This is kind of the other way around. You have a coefficient, 3, times, and then you see it's number to a variable instead of variable to a number. So number to a variable power, that's an exponential function. But it's not a power function, right? Again, a power function has the variable to a number power. So once again, not a power function. So of all these, right, there are only 3 of them that could be expressed as a number times x to a power, as a power function. And great, and that's all I have for this video. Again, the title was just identifying power functions, right? Can you look at a function and say if it's a power function or not? Does it, can it be expressed this way? All right, so I'm hoping that watching me go over these couple examples here help you when you're asked to identify a power function, if a function's a power function, on your own. And thank you very much for watching.